Okay, to understand how Rutherford basically reached his conclusion, um, excuse me, that there was a nucleus, that the positive charge was concentrated in a very small, compact region, which we now know is the nucleus, from these experiments, we have to learn a little bit about so-called scattering theory, the basics of scattering theory, and then we'll actually kind of go through um, basically the same kind of calculation and derivation that he did in order to arrive at this conclusion. So let's start with some basics in scattering theory, uh, and we'll first talk about so-called solid angles and cross sections. So a solid angle, which we denote by the Greek letter, the capital Greek letter omega, is the two-dimensional angle in sort of three-dimensional space that is subtended by a particular area from a particular point. So for example, if you're an observer at this particular point here and you look out and you see some object some distance away, and that object has a particular area that's subtended um, at that particular distance, then the solid angle omega is the two-dimensional angle which corresponds to that area. So it's in some sense it's a measure of how large an object appears to an observer looking at it from a particular distance away. Okay, so I mean, if you have some really small object but it's very close to you, then it can have a very large solid angle. It's very close to the observation point. It can have a very large solid angle with respect to that point. And similarly, a very large object that's very far away can actually have a very small solid angle subtended at a particular point. Okay. So if A is the area of a portion of a portion of a sphere, as I've indicated here, and the sphere has a radius r, um, then the solid angle omega is defined to be that area A divided by r squared, the radius of the sphere squared. Okay, so a few details. Solid angles are measured in steradians. Okay, and that's just the unit of a solid angle. We can figure out how big a steradian is by considering a sphere. If we consider the whole sphere, so if this area A, it actually covers the entire sphere. So you're talking about the full solid angle. Okay, then omega is equal to 4 pi r squared. That's just the surface area of a sphere of radius r divided by r squared, which is obviously equal to 4 pi steradians. Okay, so 4 pi steradians corresponds to the full what we call the full solid angle, the complete solid angle of an entire sphere. Okay, you can also measure solid angles in degrees or square degrees, and so 1 steradian is equal to 180 degrees divided by pi squared. Okay, and you can work out that number, but that's how you convert between steradians and square degrees, or vice versa. Okay, now we can define a differential solid angle, as I've done in this diagram. So a differential solid angle d omega defined as the differential solid angle between theta, as I've indicated here. So imagine we have some axis. We look at some angle with respect to that axis. Excuse me, O here is just the point of origin, or the point that the observation is being made from, and theta is the angle basically that you're looking at. And you have some small differential angle d theta here, which then defines this sort of two-dimensional differential solid angle d omega, which I've indicated here with the red hatches. Okay, so again, r is the distance between the observation point and the surface that you're talking about, and theta is the angle that you're looking